This video is for section 32.1. That is to say, it's on field effect transistors. The field effect transistor is a three-terminal device, and it's drawn basically like this. We have two types of field effect transistors that we'll be using. One of them is drawn with an inward arrow. This is the N FET. N for the type of doping it has, field effect transistor. The arrow points in, so N is in. The other type we have is drawn much the same way, but the arrow points out. Now, the arrow is connected to the source of the transistor. The other side is the drain. Here I've put the source on the top and the drain on the bottom. This is for PFET. Both of these transistors conduct current in a downward direction here. So for the NFET, because the charge carriers are electrons, the current flows towards the source because the electrons, being negatively charged, are flowing from the source to the drain. In the PFET, the carriers are the positively charged holes, and so they flow in the direction of conventional current flow from the source to the drain. The other terminal is the gate. The gate is what controls the current flow between the drain and the source. When the gate of an NFET is high, so when the voltage from the gain to the source is big, then the NFET is on. When the voltage from the gate to the source is small, less than a threshold voltage, then it is off. Similarly, for a PFET, we're interested again in the gate to source voltage, but source now is the most positive terminal, so we're interested in voltage from gate to source being much less than 0. And again, when it's bigger than some threshold, which is now less than 0, it is off. Okay, let's take a look at how this transistor is made. Here is a picture of cross-section of the sort of power FET that we might be using. This is an N-FET, so most of the transistor here is N-doped. The drain is connected to the negative substrate here. The source is connected to both a P plus and an N plus region here, and so this entire region up here is the source and is all connected together. And then there is what's called a channel region here. If you take a look at what's going on here, we have P-doped region next to an N-doped region, so there's a diode there. And because the source is the more positive one, this diode is reverse biased, which means there's no current flow. But the gate here, if we put a positive voltage on the gate, we can push the holes away from the surface here and bring in electrons from the adjacent regions, forming this channel that can then conduct. So when the gate is positive, it sort of locally changes the doping of the semiconductor by pushing the holes away and pulling electrons in. And when the voltage gets high enough, it actually forms a channel that can conduct between the source and the drain. That diode is actually very important, and so we often draw it in our schematics. It's called the body diode. And for the NFET, it is reverse biased this way. For the PFET, it is also reverse biased. And notice that the arrow here on the FET symbol matches the direction of the diode. So here, the diode points from the source to the drain, and the arrow points from the source into this body of the transistor. And here, the diode points from the drain to the source, and again, it points to the source in the symbol for the transistor. Okay. How do we use the transistors? Well, basically we use them as switches. And for example, if we have a resistive load like a heater, we can control it with a single NFET. When the gate voltage is low, this transistor is turned off and there's no current flow. When the gate voltage is high, the transistor is turned on and we get current flow through the resistor. So we can use this to do a simple on-off control. And that's basically all that we will be using field effect transistors for in this course, is simply we'll turn them on or we'll turn them off. The reason for doing that is we can make very power efficient switches out of field effect transistors, because when they are off, they conduct essentially no current. It's a reverse bias diode and it's got essentially no current flowing through it at all. So there is no power loss when it's off. It's completely off. When we turn it on, we can make the resistance of that transistor be very low. There's no voltage drop across the transistor other than just the IR drop for the resistance, and that resistance can be made small in a large enough transistor, the power transistors that we'll be using. So again, there's very little power loss in the transistor because the voltage drop across the transistor is very low, even if the current is high. We get the current that's lost in on transistor is basically current squared times R. That's the power loss for the transistor, and that R is the on resistance of the transistor. Often it's written as R sub on. Because we can make that very small in these transistors, we can make, again, very little power loss in the transistors. So we can make these into quite good switches. And as we'll see in the lab that's coming up, we'll be able to make a power amplifier that has very high efficiency by taking advantage of these very high efficiency switches. And I think that is it for this video. We'll talk more about field effect transistors in subsequent videos.